Welcome back to Industrial Automation course, Lecture 4, Basics of PLC Programming. Today's topics are as follows. Define and identify the functions of a PLC memory map. Describe input and output image table files and types of data files. Understand how different PLC programming languages are used. Define and identify the function of internal relay instructions. Now how to write and develop ladder logic programs. Processor memory organization. The memory space can be divided into two broad categories, program files and data files. So you could see program files and data files. Program and data file organization for the SLC500 controller could be seen in this picture. So all of the examples on this lecture is based on Allen Bradley PLCs, but the same organization could be found on other type of PLCs. So here you could see for the data file we have output and input image status, bit timer counter control, integer, a reserve network, and bit timer counter control integer. So basically this is the basically designated space memory for our data. And for the program file we have system functions, reserved user program, and subroutine programs. Program files are the area of processor memory where ladder logic programming is stored. Programming files are the part of the processor memory that stores the user ladder logic program. The program accounts for most of the total memory of a given PLC system. So we have system functions, reserve user program, and subroutine programs again. And this is our ladder logic program. And the data file portion of the processor's memory stores input and output status, processor status, the status of various bits, and numerical data. These files are organized by the type of data they contain. Okay, so you could see here the output table and the content table. For example, the same images could be found for the other type of data sets. So here in this slide, as an example, we could see memory organization for a PLC5 controller. Again, the same data organization could be found in this picture, size in elements and address range. The PLC5 and SLC500 store all data in global data tables and are based on 16-bit operations. You access these data by specifying the address of the data you want. So this is the input table and output table. The addresses in the output data file and the input data file are potential locations for I/O modules mounted in the chassis. So in the previous session, in the previous slide, we talked about the I/O module and the input and output points and how we could address I/Os based on the location. So it was one type how we could address that based on location in PLC5 and SLC500 PLCs. The status data file contains information about the processor status, and the bit data file stores bit status and frequently serves the storage when using internal outputs. The timer file stores the timer status and timer data. So we are going one by one into the category. As you could see, all of them have a file, and the data will be stored in that file. For example, for the timer that starts with T, they have their own class. For the timer is, let's say, T40. For the counter file stores the counter status and the counter data. You will see basically definition of all of these later when it comes to the counters and timers, count up, count down, downbeat, and etc. The integer file stores integer data values. The floating point file can store data that requires a decimal point. Okay, so that starts with N. This one starts with F. Again, for different type of PLCs, we might have slightly different structure, but the concept is same. The input image table is allocated to storing the on-off status of connecting discrete inputs. If the input is on, switch closed, its corresponding bit in the table is set to 1. If the input is off, switch open, the corresponding bit is cleared or set to 0. So we had this topic already in I/O lecture. Here we have one switch closed, the other one is open, and the allocation of the memory to each input and the status of those inputs, for this case 1 and 0. And here is data table file or the input image. The output image table is allocated to storing the on-off status of connecting discrete outputs. If the program calls for an output to be on, its corresponding bit in the table is set to 1. And if the program calls for an output to be off, its corresponding bit in the table is set to 0. So similar to the input, allocation of the memory, status of outputs, and the output image. Program scan. During each program scan cycle, the processor reads all the inputs, takes these values, and energizes or de-energizes the outputs according to the user program. So here is a scan file that starts at this point, scans input, it updates outputs based on the program. So it goes through the program, scan the program, and we will talk about the ladder logic program and see how it will scan the program later. Coming slides. Housekeeping, which is basically internal checks on memory, speed, and operation. Service, any communication required, so any communication to other PLCs or PC, and basically it will start over. The time it takes to complete the scan cycle is a measure of how fast the controller can react to changes in inputs. If a controller has to react to an input signal that changes states twice during the scan time, it is possible that PLC will never be able to detect these changes. So if, for example, the speed of the conveyor here is twice the speed of a PLC cycle or a scan cycle time, then basically we lose some information from the input and we cannot detect all the object. The scan time is a function of the speed of the processor module, the length of the ladder program, the type of instructions executed, the actual ladder true-false conditions. The PLC computes the scan time each time the end instruction is executed. Typical scan time data includes the maximum scan time and the last scan time. So what is this end instruction? It's basically the last instruction in our program, whatever the kind of the program is, and at the end it will compute the scan time. We'll see example of these end instructions in coming slides. Overview of the data flow during the scan process. So here we have one example. Input modules send the input data and the input image table file will be updated in the memory of the PLC. And then it will basically examine the data. So it check, compare, examine specific conditions on the program for the contacts. So we have normally open, normally closed contacts here, and those will be, the status of them will be updated based on the input image table. And then the output or the coil will be updated and the result will be returned to the output image table. And then the output data will be sent to the output module for energizing and de-energizing or field devices. Scan process applied to a single rung program. So here we have a single rung program. So here a processor memory, the data we have, input image table, the output image table, and or program that contains only one rung, and that includes only one input or one contact here and one coil, one output. The contact is corresponded to the input device or the switch. The address is I36 and the output coil is corresponding to the output device here, and the address of that is 047 in that output image table. Once the switch is closed, the status of the contact will be updated. Based on the program, then the coil will be true or on, and then the image file will be updated and that data will be sent to the output module to energize or output device. Scan process applied to a multiple rung program. So here we have multiple rung program. You could see the same loop. We have inputs from the input module and the input image table will be updated based on the real status of the inputs. Then that will be executed on the program. All the contacts will be updated, and it goes from rung to rung and will update each of these coils or outputs. When the scan cycle is finished, so it comes to the end instruction. So we have start and end. So when it reaches to the end instruction, the one scan cycle is finished and the output image table will be updated, and that information will be sent to output module to energizing and de-energizing or outputs. Okay, so in this slide you will see how the scan pattern works. So does it go vertically or does it go horizontally? So the title is a little bit confusing. We don't have vertical versus horizontal scan pattern. We have, let's say, the kind of hierarchy. So it goes first horizontally and then vertically. So let's say this is our multiple line run program, ladder logic program. It goes from first rung, it finishes the first rung. Okay, from this contact, then we'll update the coil, the first coil, then it will move on vertically to the next rung. It will read the contacts here based on the logic. It will update the coil, and then again we'll move vertically to the next rung. Yes, and here we have a parallel branches here, so it will read these branches at the same time, and then we'll update the coil, and then when it reaches to the end, one cycle is finished. Yes, so we should know that the program is going rung by rung and updated the coils one by one vertically. PLC programming languages. PLC programming language refers to the method by which the user communicates information to the PLC. So here we have a very nice flowchart that shows standard PLC programming languages. And you could see it's divided into two main categories: textual language and graphical language. Textual languages are instruction list and structured text. So instruction list or IL and structure test or ST. On the other branch, we have graphical language, and you could see we have ladder logic programming or a ladder diagram, functional block diagram or FB diagram, and sequential function chart or SF programming. Yes. Sequential function chart also is called graph programming. Ladder diagram language is the most commonly used PLC language and is designated to mimic hardwire relay logic. So it basically mimics the wiring between contacts and relays. Here we have hardwire relay control circuit. We have switch 1, push button 1. We have a control relay 1 and control relay 2. We have solenoid and we have limit switch. And the way they are connected, each other. And we have equivalent ladder diagram program. In the equivalent ladder diagram program, you see that we have push button, we have control relay, we have one control relay, two, we have solenoid, and we have limit switch. So inputs are in the form of contacts and outputs are in the form of coil. So you see the tags are assigned to each contacts and coils, and each of them have an address in the memory. Instruction list programming language consists of a series of instructions that refer to the basic and, or, and not logic gate functions. So we have the same hardwire relay control circuit here, and we have IL program or instruction list program. This program is equivalent to the ladder logic program that we had in the previous slide. So here you see that start here with the push button and control relay 1. So if the push button and control relay 1 both are true, or so or instead of this we have this parallel branch here, or the limit switch 1 is closed or true and not, so then we have the negated contact here, control relay 2. So this one is in series with this part and not CR2, then the solenoid output will be true. So if the logic here holds, if we get true on this logic, then we will get also a true or output, or the output solenoid will be on. Okay, so here we have a function block diagram programming that uses instructions that are programmed as blocks wired together to accomplish certain functions. So here we have the ladder logic program, and here we have the equivalent function block, or FBD programming. So here we have a Boolean AND function block, and if A and B both are correct, the output of this block will be true. Here we have parallel branches, which is equivalent to the OR, and we have again here two contacts in series, which is equivalent to the AND, but one of them are negated. So we have this circle here that shows first the B should be negated before going through that Boolean AND function block. Ladder diagram and functional block diagram programming used to produce the same logical output. Okay, so here we have same equivalent programs. For an example, equivalent of the ladder diagram program. So we have two sensors or two contacts, and we have one coil, which is the pilot light. And here we have a function block, which is a Boolean AND function block that gets two input, 1 and 2. If both of them are true, then the output will be true. Otherwise, the output will be false or 0. So this function block is equivalent to this ladder logic program. And finally, we have sequential function chart programming language, which is similar to flowchart of your process. Okay, so it's very intuitive. They also call it graph programming because it's based on a flowchart of the program. The program is split into steps with multiple operations happening in parallel branches. So we have the initial step, or initialization here, and then if the transition condition holds or is true, then it will move on to the step 2. We have some actions here in step 2, some updates of outputs based on inputs. Again, we have another transition here and goes to the step 3. Here we have a basically parallel transition, and if this one doesn't, if the output of the first transition is not true, it will move on to the second transition and will go through this loop. Otherwise, it will move to the step 3, will execute the actions in the step 3, and finally, if the last transition holds, then the program will be finished at this point. A structured text is a high-level language primarily used to implement more complex procedures. So here we have the ladder diagram program, and here we have equivalent structured text program. So this structured text program is very similar to conventional programming like C or C++, I don't know, Python or Pascal, these type of programming languages. So here you see one equivalent structured text program for this ladder logic. If sensor 1 and sensor 2 are true, then the solenoid 1 will be updated and the value of the solenoid 1 will be 1. Else if this one is not true, then it will check the second condition. If the second condition is true, which is sensor 3 and sensor 4 and not sensor 5, this is the negated of the sensor 5, then also solenoid 1 will be updated and will be equal to 1. If none of these conditions are true, then the solenoid 1 status won't change and will stay as false or 0. Relay type instructions. The ladder diagram language is a symbolic set of instructions used to create the controller program. Representations of contacts and coils are the basic symbols of the logic ladder diagram instruction set. Okay, so these contacts represent inputs and coils represent outputs. The examine if closed or XIC instruction looks and operates like a normally open relay contact. So here we have XIC instruction, okay, or basically the basic form of instruction we have in ladder logic, and it's based on the normally open relay. Here you see that when the switch is open, the contact value is 0, and when the switch is closed, the contact value will be 1. Associated with each XIC instruction is a memory bit link the status of an input device or an internal logical condition in a rung. So, for example, this switch has its own contact. That contact has the bit address of this input, and the second one also has its own contact, and we need to associate the bit address of this input to that contact. The memory bit is set to 1 or 0 depending on the status of the input. A 1 corresponds to a true status or on condition. Okay, so the switch is closed here. So our XIC contact will be true, and the status will be updated in the memory image file as 1. So you see the address we located to the memory is I14, and in our programming we chose that address for this contact. These green bars shows that the contact at this moment is true. If the instruction memory bit is a 1 true, this instruction will allow run continuity through itself like a closed relay contact. A 0 corresponds to a false status or off condition. So just the opposite of what we had in the previous slide. Yes, so the switch is open and the status of the contact is 0. So it does not allow run continuity because the contact is open. The examine if open instruction looks and operates like a normally closed relay contact. So this one is opposite of XIC, or we could say that this one is negated of a normal contact. This is a negated sign. The instruction asks the PLC processor to examine if the contact is open. So the other one checks if the contact is closed. If it's closed, then it's 1. But this one checks if the contact is open. If the contact is open, then the status of XIO is true. It does this by examining the bit at the memory location specified by the address for a 0 or 1. So in XIO, as with any other input, the memory bit is set to 1 or 0 depending on the status of the input. A 1 corresponds to a true status or on condition. Okay, so if this one is true, then we have 1. So regardless of the type of contact, is XIC or XIO. If it's true, the status is 1. But what is exactly the real condition or status of the switch or the input? Yes. The instruction is interpreted as false when the bit is 1. So here the bit here is 1. If the bit is 1, then the status of the contact will be false or 0 and will not allow run continuity through itself. So it's basically just opposite of XIC. And here we have for the XIC, we have open switch. 0 corresponds to off condition, and the function is interpreted as true when the bit is 0. So the switch is open, bit here is 0. Okay, so the bit is 0, but the status of the contact will be 1, and it will allow run continuity through itself. So it's now the contact is true. That's why we have these green bars here, and we have continuity of logic. The output energize or OTE, output energize instruction, looks and operates like a relay coil. So this one is an OTE or relay coil. This instruction signals the PLC to energize, switch on, or de-energize, switch off the output. The instruction is associated with the memory bit that energizes the output when set to 1 and de-energizes the output when reset to 0. Okay, so in this slide you could see one ladder logic program. We have two inputs, I11 and I14, and we have one output. And here you could see the wiring. We have two limit switches. On this example, both of those switches are on. So we have one on the memory input data. And since the logic is valid, the logic pass is valid, the output also will be true and 1. So OT instruction is set to 1 to energize the output, and a true logic pass is established by the input instructions in the run. Yes, so we have the true logic pass here. This one is true, this one is true, and finally the output is true. On this slide, we have only one output, and this is the ladder logic program, one input, one output. We see basically how it works. So a signal present makes the normally open bit 1 true. A signal absent makes the normally open switch bit 0 or false. The reverse is true for a normally closed bit. So here we have this one, a contact and normally open. So when the switch is open, the output is false. Normally closed contact, on the other hand, is true because the switch is off or is not closed. And you see basically the reverse reaction when the switch is closed. The main function of the ladder logic diagram program is to control outputs based on input conditions. Each contact or coil symbol is referenced with an address that identifies what's being evaluated and what's being controlled. So contacts shows that what we should evaluate. We should evaluate the status or condition of the switch or input. And coil shows that what we should control. The same contact instruction can be used throughout the program whenever that condition needs to be evaluated. For an output to be activated or energized, at least one left-to-right true logical path must exist. So that's very important, that we should always go through the wrong from left to right. Yes, so from left to right. A complete closed path is referred to as having logical continuity. So let's say here we have 3 rungs, 0, 1, and 2. On the first one, the first contact is false. The next two are true. So logical continuity doesn't hold here. The path is not true and the output is false. But on the other hand, the wrong one, the logical path is true. We have logical continuity and the output is true. When logical continuity exists in at least one path, the wrong condition and output energized instruction are said to be true. So you see, at least in one of them, which is wrong one, the logical continuity exists and the output is true, yeah? But let's see what's happening in wrong 2. So we have a parallel branch here, and this one, logical continuity doesn't hold, but on this path, it holds, yes? So we have also 2 outputs, and at the same time, both of them will be true at the same time. So you see, we are moving from left to right.